if the spacecraft releases a box with chocolates, let's say, what's going to happen is you're going to see that the box is going to fall with acceleration 9.8 if you're on the planet Earth and if there is no air. And eventually, this parcel, this box is going to end up under the spacecraft. Now, what would have happened if the spacecraft were not at rest, but traveling with constant velocity in horizontal direction? So some constant horizontal velocity like this. And in mid-flight, it releases the same box with chocolates. But what would happen is that, well, the box with chocolates is going to fall along some parabolic curve, normal parabolic trajectory. But what is interesting is that during the free fall of this box, at any moment of time, the spacecraft is going to be exactly above the box. So what can you conclude from this? You can say that the fact that the spacecraft was moving in horizontal direction didn't affect at all the motion of the vertical motion of the box. The box was still always exactly under the spacecraft. In other words, the horizontal and the vertical motions are completely independent. They don't know about each other. They don't affect each other. Well, let's do another experiment of the same type. Let's say that you are after physics class, you feel excited about what happened in class, and you take your you go to your pickup truck, and of course, we're in Idaho. On the back of the truck, you have a gun rack, right? You grab the rifle from there, point it vertically up, and you shoot around in vertical direction. Now, assume that there is no air resistance, wind, there is no rotational motion of this bullet. Where is this bullet going to end? Well, it's going to go up. And where is it going to end? It's going to fall back exactly on top of the rifle. Exactly, right? In the ideal case, if you aimed exactly in vertical direction, this is what should happen. Well, now imagine you do the same thing, but your pickup truck is not at rest in the parking lot, but your pickup truck is moving with constant velocity on I-15, moving with 80 miles per hour on I-15. Well, you keep the wheel with one hand, and with the other hand, you point the rifle directly upward, and again, you shoot a bullet in vertical direction. You're in motion, constant velocity along a straight line on I-15. Where is this bullet going to end? In front of the truck, or on top of the barrel of the rifle? What would you say? Go ahead. Feel free to.
On top.
On top? Why on top?
There's the vertical component and the horizontal component are independent. So
Okay.
just like that, the opposite.
Are you tempted to get outside and try this experiment? See if your prediction is correct. No?
We have an answer in here too.
Okay, great. So make sure that people that answer go to the link that I sent on Google Docs and put themselves an extra brownie point. Look, the easiest thing is everybody to take care of his brownie point or her brownie points, because otherwise we have to ask what is your name and so on. And sometimes it is just more convenient if you take care of the brownie points yourself. Just be honest, of course. So anybody tempted to go and try that experiment? You're tempted?
Well,
do you have the pickup truck?
I don't know that I'd try it on I-15.
Okay.
I'd probably try it on like on back road.
Well, there are all kinds of complications in real life. There is air resistance. There is the bullets. The bullets have, well, Pocatello cops are not so bad in general. Right? They can cut you some slack if they figure out that it is in the name of science.
Yeah.
But luckily, we can do this experiment right here in the classroom. So here is my pickup truck, and on top of it, I have the rifle. Well, some rifle, well, it is still a good. And we can make this pickup truck move more or less with constant velocity along a straight line on those rails. But the rifle is. Where is the on switch here? Oh, oops. There it goes. Well, luckily this bullet is plastic, so nobody got hurt. Right? It is on. Yep. Okay, let's try it.
Yeah. The videos real quick.
What was that?
Can you switch the videos real quick?
Yeah.
Okay. Well, maybe we may want first to shoot the bullet in upward direction. When the truck is at rest, let's do it. It's not very well aimed, but
Yeah.
you know that when you're with guns, it is important to have the right aim and safety precautions. Well, more or less it is a little bit this way, but now let's see what's going to happen with the bullet when the pickup truck is in motion with constant velocity. Yeah.
So from the two times you have fired it, it's always gone this way.
Yeah, because it is not completely, it is a little bit under angle, unfortunately. And there is a way to adjust it, but it will take some time. So I'm still going to see if I'm going to get exactly the same result when the pickup truck is moving. Let's see. Oops. Huh. It didn't. It didn't fire. Sometimes rifles misfire. So it happens. Let's make sure that. Huh. Okay, let's try it again.
better?
Is it the speed or if it is the trigger a little bit out of, not getting through the. Okay, let's give it a shot. Slow. I think there is something wrong with the track. Okay. It should be a little bit. I think that this experiment would be much easier with this device rather than with the real rifle. So what's happening is that this trigger is not in this direction far enough. Oh, see? Oops. Okay. Let's try it again. Okay. Yeah, maybe just estimate it a little bit.
If you go up to the top of the list, then this video should be.
Is he doing it on the,
Do you
oh,
know?
yeah.
Don't.
This is
I can just push it like this.
okay. Something is wrong with those bullets. Maybe a little bit bigger, or maybe in different spots. Okay, next time we should try this with the real gun. Okay, let's give it another shot. Yeah. Maybe bend it from this side a little bit. Yeah. Oops. Yeah. But now you saw that the bullet pretty much hit the rifle right in the barrel. Again, what the conclusion that you can make is that the presence of horizontal motion didn't affect the vertical motion at all. The bullet ended exactly on top of the rifle, just like in the case when the truck was addressed. Well, this gives you an idea that in the case of a motion of an object, projectile, bullet, any object that is not moving along a straight line, but still moving with constant acceleration, you can separate the horizontal and the vertical motion and treat them completely independently, as if horizontal motion is not present, or as if the vertical motion is not present. Just separate the components of all vectors, and the formulas that we proved for linear motions, for linear motion with constant acceleration, should work for motion along any curve with constant acceleration. So this means that the formulas that we had, so those 4 formulas, you just have to apply them by components and they should still work perfectly well. So let's say, let's try those formulas again, and for the last time maybe. So the first formula says that final velocity is initial velocity plus acceleration multiplied by time. This formula applied by components of the vector quantities present is going to look like this. The x component of the final velocity is equal to the x component of the initial velocity plus the x component of the acceleration, and that's it, multiplied by time. The same formula for the y component of the motion is going to be like this. Vy is equal to v naught y component plus acceleration y component multiplied by time. The second formula, which says that the displacement is equal to, what was it? 1/2 of initial velocity plus final velocity. Let's make it like this, multiplied by time. The same formula by components is going to look like this. Or the y component looks like this. The y component of the displacement is again 1/2 of initial plus final velocity y components multiplied by time. The next formula, displacement x component is v naught x t plus 1/2 acceleration x component times squared, and similarly for the y components. V naught y t plus 1/2 acceleration y component times squared. And the final formula, the final velocity x component squared is equal to initial velocity x component squared plus 2 times acceleration x component multiplied by x component of displacement. And you have the final formula for y components. Looks like this. Multiplied by y component of the acceleration. This is y component of.
That's going to be the.
Say it again. Ay times y. Y is the y component of displacement. So those are the formulas that should work thanks to the fact that the two perpendicular directions along x direction and y direction do not affect each other. This is why the composition of vectors in components is so important. You can think about the two directions, x direction and y direction, as independent worlds. You don't know what is happening if you're in one of the worlds in x components. You don't know and you don't care what's happening in the y components, and vice versa. Separate worlds with no connection between each other, and you have to treat them as separate worlds. Okay, any remarks and questions? Let me see some example how to use this. So this is, of course, theory. Let's see how would this work in some practical cases. So you noticed probably that I didn't give definitions, like chapter 3 starts with definitions for displacement in 2 dimensions, velocity in 2 dimensions, accelerations. I skipped that section because I talked about those things in chapter 2. In chapter 2, we gave the general definition for velocity, displacement, acceleration. So we don't need that at this moment of time. Okay, let's start with a simple exercise. And the exercise looks like this. Well, we can do it with rifles, but let's be a little bit more pacifist a little bit. Let's say a football. And so the example looks like this. You have a projectile, a football or a baseball or some projectile, and you launch it from ground level, let's say, with certain velocity, under certain angle with respect to the horizon. The question is, what would be the range of that projectile? How far this projectile is going to get? So let's see what we have. So here is the ground level. Here is the initial position of your projectile. And you launch it, and the projectile, of course, is going to go along some parabolic trajectory like this. It's going to end here. So let's see what is given to us. Let's say that you are given exactly the launch velocity, both in magnitude and in direction. So the launch velocity has to be tangential to the parabola, to this curve. So the launch velocity looks like this. It is a vector like this. V naught vector that is at the initial point, tangential to the parabola at the initial point. So you're given both the magnitude, V naught is equal, let's say, to 15 meters per second, or some other number, whatever. And let's say that you're given the angle, the direction of the launch. So this angle is angle theta. Maybe angle theta is 10 degree or something. Any number of degree you want.
Real quick, Braden, could you move the camera a little bit over to the right?
Just rotate the
No, the camera is
Thanks. That's better.
with the laptop. Okay, good. Is this any better picture?
That's better.
Yeah, it does produce a better picture on the whiteboard.
Okay. Okay. So this is what you are given. The question for us is the range. What is this distance? Right here, from here to here. So you see the pattern how you approach the problem. You say you write down what is given in the problem. Sometimes what is given is going to be more clear if you have the diagram. Almost always you have to have some diagram. Well, this diagram is okay, but of course, in order it to be a real diagram, it needs a coordinate system. So you have to select and show a coordinate system. Otherwise, the diagram is worthless. So how to choose the coordinate system? Well, the origin of the coordinate system is convenient to be at the launch point, and take the x-axis of the coordinate system horizontal and the y-axis of the coordinate system vertical. So in this coordinate system, the range of the motion is exactly x component of the displacement. Actually, the displacement vector is this vector right here. And that vector has only x component. Its y component is zero. So this is the x component of displacement, and this is what we're looking for. X is what? Well, let's follow the procedure here. I have to clean the board and see if we have sufficient information to solve this problem. Again, the idea is all vectors that are given have to be decomposed to their components, x and y components. Well, this means that this initial vector, initial velocity vector, let's make it bigger so it to be better visible. That initial velocity vector has to be decomposed into, here is the y component of that vector, call that initial velocity y component, and here is the x component right here, the initial x component. Of course, the two components are perpendicular. Looking at the triangle that you constructed, you can say that, well, since the angle is known, and since the hypotenuse of the right triangle that is formed is also known, you can say that the x component of the initial velocity is exactly equal to the magnitude to the hypotenuse of the vector multiplied by cosine of the long triangle, which is 10 degrees, it is known. In a similar manner, you can say that the y component of initial velocity is equal to the hypotenuse v naught multiplied by the sine of the long triangle. Again, this comes directly from looking at the triangle. Well, this doesn't seem to be any sufficient information. Practically, we have only one number that is known for the x component of the motion, and we have only one number that is known for the y component of the motion. However, this is a projectile. This is an object that is in a free fall in the gravitational field of the planet Earth, no air resistance like always. So you can make the argument that you know the acceleration of this object. Since it is an object in a free fall close to the surface of the planet, its acceleration is 9.8 directed downward. So you can say, well, at any moment along the motion, the acceleration is this. Acceleration is 9.8, or the number g in the way it looks like in downward direction. Well, if the acceleration is completely in downward direction, in negative y direction, what is the component of this acceleration vector in x direction? Well, it has zero x direction component. It is completely vertical. Well, so we have a little bit of a progress here for the x component of the motion. In a similar manner, you can say that the acceleration y component is what? 9.8. But look, this orientation of the coordinate system says that vectors that are pointing up are positive, vectors that point down have to be negative. So the acceleration y component has to be negative 9.8. Negative 9.8, and I'll use the letter G for 9.8 for short. Okay, so we have two numbers for the x motion, we have two numbers for the y motion. Well, in order to solve any of those two independent motions, we need three numbers, as you remember. We need three numbers in order to successfully apply one of the four formulas that are that we have. And look, see the y component of the motion, the y component. So this, make it Vy here, I'm sorry, Vy. V not y, initial velocity. Right, please fix that because it doesn't make sense. But now, can you tell me if, well, this is clearly the displacement vector. of the projectile. What is the displacement, y component of this displacement vector? 0. In y direction, this projectile didn't do any displacement. So here it is. Now we have 3 numbers for the y components of the motion, and therefore we can find whatever we want for the y component of this. Well, you may not be very excited to learn what the y component of final velocity is. You actually can guess it. So you don't need to. The problem is not asking about it. But you can calculate, let's say, the time of flight. You have 3 numbers. You're looking for the time of flight. In other words, you have to apply one formula that doesn't include which variable. Final velocity y component is, and if you look at the list of the formulas, final velocity is not present in this equation. Displacement is equal to v naught y time plus 1/2 acceleration y component t squared. So you have to, in this equation, the only unknown is the time, and you can solve for it. Unfortunately, it is a quadratic equation, but we're lucky again. It is not a full quadratic equation because the y component of displacement is 0. So you can say 0 is equal to v naught y t plus 1/2. Well, instead of, okay, acceleration y component t squared. And now if I factor out the unknown time t, I'm going to get 0 is equal to t, the factor, and you have v naught y plus 1/2 acceleration y component t in the brackets. Now the time of flight is clearly not 0. I can divide to that non-zero time of flight, unknown, but non-zero time of flight. And the equation now is going to read 0, right? 0 divided by t is still 0. So I have 0 is equal to the expression in the brackets, v naught y plus 1/2 acceleration y component t. And now let's substitute the initial velocity y component and the acceleration y component with what they're equal to. So you say 0 is equal to v naught multiplied by sine of theta plus, or it's going to become minus 1/2 g multiplied by time. And now this is a linear equation with one unknown, and you can directly solve it. So solving it is move this to the other side of the equation with opposite algebraic sign and solve for t. So you're going to get something that looks like this. Negative v naught sine of theta is equal to negative 1/2 gt. You can multiply both sides by -1 to get rid of the minus signs if you feel like. And you can divide both sides to 1/2 g, and you get that the time of flight is equal to 2 times v naught sine of theta divided by g. This is the time of flight of your projectile. You can substitute the numbers and get some numerical value if you want, but the problem is not asking us what is the time of flight. The problem is asking about the range. So we have to go back and solve the x motion completely and figure out the value of the x component of displacement. Now we have three numbers for the x component of the motion. We have the time of flight. It is this number, 2 times v naught times sine of theta divided by g. Here are our three numbers. And what is the x component of the displacement now? Well, look for a formula that doesn't include what? Final velocity. And that formula is exactly the same, but for the x component. So let's do it. So exactly the same formula like before, but now for the x components. So the formula is going to read, the displacement x that we're looking for is equal to x component of initial velocity plus acceleration, x component, and so on. Well, this formula is much simpler than it looks like, because the acceleration x component is what? 0. This means that this entire term is 0. Now, then the displacement is exactly v naught x t. We know t, we know v naught x. Well, let's substitute that. You get displacement is equal, v naught x is v naught times cosine of theta, and the time is this expression. 2 times v naught multiplied by sine of theta divided by g. And this is the answer. If you want, you can get a numerical value for the range. It is desirable you to write this answer in a little bit simpler form to be easier to plug in the numbers in the calculator if you want to do that. So v naught times v naught is v naught squared. So you get v naught squared multiplied by 2, multiplied by the sine, and multiplied by the cosine of the long triangle, all of this divided by g. You can leave it this way, or if you want to simplify a little bit further, there is a formula in trigonometry which says that 2 times sine of any angle multiplied by the cosine of the same angle is equal to what? It's equal to sine of double the angle. So if you use that trigonometric formula, if you feel like using it, you can write the final result like this. The x component of the displacement is equal to v naught squared multiplied by sine of twice the long triangle theta, all of this divided by 9.8. And this is your answer in analytical form. You can substitute numbers and get the range of this projectile. It is a long problem, and I intentionally solved it. Well, there are simpler ways, faster ways to get the answer. But if you sit down and write down at some point independently, once or 2 times or 3 times this solution, you're not going to have any more problems with chapter 3. Chapter 3, this is the most challenging part, projectile motion, most challenging part from chapter 3. Easier ways to solve this problem. There are multiple faster ways, but this one is covering practically everything that you may be asked in the case of projectile motion. Let's see some easier shortcuts to solve the same problem. Well, the shortcuts are based on the properties of the projectile motion. You recall that in the case when we talked about a projectile that is launched vertically upward, there were some symmetries. So here it is, projectile that is launched vertically upward goes up and comes back exactly with the same velocity in opposite direction though. So if the initial launch velocity was v0, only y component, the final velocity of this projectile is negative v0. The same magnitude, but in opposite direction. At the top of the trajectory, the velocity of the projectile is exactly 0. And anywhere in the middle of the trajectory, if on the way up the velocity is v, on the way down at the same point, the velocity is going to be negative v. The same in magnitude, but in opposite direction. This is for projectile that is launched vertically upward. You can draw similar diagrams for the case when the projectile is launched under angle. So the symmetries in that case are going to look like this. Let's say here's the axis. Let's say you launch from here. The trajectory is going to be part of a parabola. So look, it looks easy when I draw it on the board. If you don't draw it yourself independently, you're going to feel completely frustrated when a similar problem appears on a midterm or whatever. So I would recommend you to draw independently a diagram like this. The tricky part in this diagram is to put the launch velocity v0 appropriately. Tangential, the velocity vector is not something that you see. It is exactly the vector that touches the parabola in one point, the initial point. Okay, now the symmetries. Well, if you look at the components of the initial velocity vector, v0x is here, v0y is here. The two components are seen by drawing the right triangle, drawing them and forming the right triangle. You can use sine, cosine if you want now. But let's talk about the symmetries. Look what happens. The x component of the launch velocity doesn't change throughout the entire motion of the projectile. It stays constant. Well, in the vertical motion, that constant was 0, but now that constant is exactly this vector. Everywhere along the motion, the x component of velocity has exactly that value as the initial x component of velocity, including at the top of the trajectory. At the top of the trajectory, the velocity vector is going to be, well, the y component disappears exactly like it disappeared here, but the x component is whatever it was in the beginning. And similarly, at the final point of the trajectory, the velocity vector looks like this. And its x component has exactly the same value as it had before. v0x is vx, exactly the same value all the time for the x component. Why? Because in x direction, there is no any acceleration. There is no any effect of anything because we don't have air resistance. There is nothing pushing this object to speed up or nothing to slow this object down in x direction. Well, for y directions, well, the y component of the launch velocity, well, it changes. As the object goes up, the y component gets smaller and smaller. At the top of the trajectory, the y component of velocity turns into 0, exactly like in this case. And at the final point of the trajectory, the y component of velocity has exactly the same magnitude like during the launch. So it is like v naught y, but in opposite direction. So this vector is exactly in opposite direction to this one, but with the same magnitude. So using the symmetries present in this projectile motion, the problem that we solved can be solved much faster. However, those shortcuts are not always available, as you're going to see when you start solving homework problems, for example. So you're going to encounter problems where the shortcuts are not exactly applicable. But the long solution that I gave is always going to work. Let's see questions and remarks. Okay, keep your questions in that case for Wednesday. I'll post the links that were missing. And the homework assignment on chapter 3, we probably have to move it for later time because there were some people that couldn't figure out how to get in touch with customer service at WebAssign. So please look at the homework problems, and next time you should have many questions. Don't forget to assign yourself brownie points if you participated in the discussion, online or offline.